So also on my behalf, good morning everybody. I will do the second part of the tutorial and we will now make the switch from statistics to machine learning. And I'm going to talk about what we call first order uncertainty representations. Those will be like the classical probabilistic models that you know. And because of that, I will also mainly be talking about how to evaluate this model. So my part is actually separated into three subparts. In the first subpart, I will talk about those probabilistic models and how to evaluate them directly. In the second part, I will talk about if we construct sets from those probability distributions, and I will explain later what that means. And in the third part, I will then make the extension for regression. So the first two sections are basically binary and multi-class classification, and then the third part will be regression. So let's start with introducing a bit the notation I will be working with. So we will have the typical supervised learning setting where we have an input space X and a label space Y. So for classification, our label space will be in multi-class classification. We have K classes 1 to K. In regression, it will be typically the real numbers. And then we assume we have a data set that is IID sampled according to an underlying distribution that we don't know, P. And in addition, we will analyze the conditional distribution. So if you have that joint distribution, you can also construct the conditional distribution of the labels given X on the ground truth level. And a probabilistic model I then define as a kind of estimate of that conditional distribution. So I will use the notation throughout the presentation, the P with a hat on top of it. And for multi-class classification, I will have a bit of a specific notation because we will need a vector notation there. So in multi-class classification, you predict a categorical distribution for every X. I will use there the notation this bold P with a hat if it's the predicted distribution. And this consists of the components P1 till Pk. And so you can do the same then for the ground truth distribution. That will then be the P without the hat. And so both the predicted distribution and the ground truth distribution are actually probability distributions over the probability simplex, which is defined so as all distributions for which it holds that the probabilities together sum up to 1, and all of the probabilities of course smaller, bigger or equal to 0. Okay, let's start with a couple of classical examples of such probabilistic models. I have two of them. Decision trees. In a decision tree, what are you going to do? You take your feature space and you're going to separate them in rectangles. These are the splits you make in your decision tree. So on the left-hand side, I have here an example for binary classification where you have this kind of separation of your feature space that corresponds to, in your decision tree, different splits you're going to make. Now you can grow this decision tree till really the fully end where you have pure leaves, but then the probabilities that you're going to estimate are not going to be good probabilities. So typically you will stop earlier, like in this example here. The leaves that we get are not pure here. And we have, for example, if you take one of those leaves, how does this work here? Oops. If you take, for example, this one over here, we have 3 instances of the black class. We have 1 instance of the, no, sorry, I can't see it very well from this side. Let's stand here. So you have, here in this case, I see, some instances of the black class and some instances of the red class, and from that you can compute your probability that you are red or black. So the question is, for such a probabilistic model, are those probabilities correctly represented or not? Are they a good representative of the ground truth distribution P? I give a second example. In neural networks, we do something a bit similar. Let's say we have an input here of a flower as input to our neural network. Then we have those feature extraction layers. Then we have a final layer for classification that's typically a softmax, so that you end up with probability. So the output of your classifier is going to be this, for example, this distribution here, where you kind of say it's a high probability that it's this type of flower, and it's a high probability that it's this type of flower, so you're quite uncertain, which might be the case because of the fact that this image is here taken with kind of very bright conditions, so you didn't have a very good picture of the image. And in this example here, this was an image of the class Vinca Major. So the kind of ground truth that you give to the classifier is this thing, which is not really the ground truth distribution that belongs to that image. You have only observed that one image, but if you would observe actually from the image itself, you cannot really deduce the class label for it. And this already gives a typical issue why in deep neural networks those probabilities will not always be correct. So what you do in deep neural networks then with such training data, you're going to minimize a loss function, which is typically the cross entropy. So I have here the true probability distribution, the predicted one. And as the true, you consider this kind of Dirac distribution, which is not the real true distribution, but because you only have observed that one image, it looks like a Dirac distribution. And this cross entropy you can decompose as the entropy of P, which is a constant, and the KL divergence between P and P hat. And you want to minimize that. So what you basically want to do is you want that this probabilistic model looks as similar as possible to this here. So you're going to get overconfident predictions. It's well known in neural networks that they lead to overconfident predictions with other models as well. And this typically happens because those models are of high capacity so that you really can overfit them in a way with respect to the probability distribution that you fit. So this is what you then typically see is something like this. So if we have the predicted probability on the horizontal axis and we have the true probability, if you would know the underlying distribution on the vertical axis, you get this kind of overconfidence. For binary classification, either you predict too much that it's confident for the positive class, or here on this side, you predict with too high confidence that it's the negative class. This is here another example of what can happen. Here you have a systematic bias towards the positive class, so it predicts more towards the positive class. So this is a kind of phenomenon that you don't want to see. So in the classification literature, they say that this model is not going to be calibrated. So what's the mathematical definition or statistical definition of calibration? I have it here. So I will have several of those definitions also for multi-class classification. So it's always going to be important in those definitions to look at the condition. We have a condition here. We look at the probability conditions that our predicted probability for class 1 is a certain value alpha. Then what we say, if that value is alpha, then we should observe that the label is 1 according to our underlying distribution should also be alpha. So to say it in a different way, for all the instances that you predict probability 0.6 that it's the positive class, when you then look at the data that comes from the underlying distribution, you should really have an accuracy of 60%. Then those probabilities are kind of well calibrated. Yes?
This is a tutorial. Let me ask a question to the Willem showed this example of a decision. So what is the best way to train a well-calibrated? Should you grow it star, or should it be relative or decision tree in the XP decision sum? With only a single split, or maybe no split at all, just a root node. So look at the definition. Who's in favor of a big tree? And many splits, so that each node can estimate very basic. In between of another project. Who is in favor of a big tree? is in favor of an intermediate tree. Okay, two. Who is in favor of a very small tree, just single root node? Roughly 1/2, but it does, I think, a little bit in favor of the last option, and this is correct, right? Because then you only have one alpha. And it's a relatively useless predictor, but it is calibrated according to that definition. Falling a little bit into question the definition itself. Sorry.
Okay, well, it's a good remark, Eike. So indeed, I didn't say that. Calibration is only one property of your classifier. And of course, you also want a classifier that has good predictive performance. So there might be a trade-off between the two. So of course, this definition is on the population level. You take this probability that you see here over a random XY pair from the underlying distribution, and we don't know the underlying distribution. So when we have a data set, we'll have to estimate this probability to see whether our classifier is calibrated. And the classical way of doing that is with so-called reliability diagrams. So what are you going to do? You're going to have here on the x-axis your predicted probability, and you're going to separate that into bins. And then for your instances that you have in your training data set or in a validation data set, so typically you're going to do this on a validation data set, you're going to look at the observed frequencies in each bin. And ideally, the observed frequency in each bin should corresponds to the predicted frequency of the bin. So for example, the example here on the left-hand side is better calibrated than the example you have here on the right-hand side, where the predicted frequencies deviate quite a lot from the observed frequencies. And to put that in a formula, so what you do is you can compute the expected calibration error, where you take the average over all the bins you observe. And in the bins, you look at the difference between observed and predicted probability for the positive class. So observed, what is that? This is of all your instances in your data set, how many times you see the label 1. So this yi here is encoded as either 0 or 1 for the positive class. And then the predicted probability in that bin is actually the average predicted probability, because the probabilities might not be uniform in that bin, so you still need to also compute that. And then you take just the difference between those two. And this is a classical measure to measure this calibration. Okay, that's for binary classification. And now we can extend this for multi-class classification. And for multi-class classification, there's in total 3 extensions in the literature, going from weak conditions to stronger conditions. So the first one is called confidence calibration. And confidence calibration is a very weak condition. So what it means basically is you're only going to look at the highest probability. So remember, for multi-class problems, we now have this probability vector P that we predict for every instance, which is a vector in the probability simplex. And we're now going to condition on the fact that if the maximum of these probabilities over the classes, so the class for which you predict the highest probability, if that value is alpha, then you should also observe instances of this class K alpha times. So this is now, you have multiple classes, and if I predict, for example, for all the instances of which I predict probability 0.6 for the highest class, doesn't matter which class it is, for the highest class it's 0.6, then I should be correct. I should see that class with 60% of the times. So I should have an accuracy there of 60% of the times to put it correct. So again, this is on the population level, so this cannot be measured on a data set. So what you do is you're going to estimate this, and it's exactly the formula as we had on the previous slide. The only difference here is that we now look at the accuracy in every bin, and we look at the average predicted highest probability for each of the bins. So you're going to do the binning now according to those maximal probabilities. So that's called confidence calibration. Then you have class-wise calibration. That's a stronger notion. now we're not only going to look at the highest probability, but we're going to look at all the k probabilities when we have k classes. So you have there a condition that needs to hold for all the classes k. And what we're going to do is it's a kind of one versus all decomposition. So for every class, we're going to see that as the positive class, and then you're going to repeat what you had for binary classification for that class. So that means that the binning also will have to be done for every class separately. So in the definition, what do we get? We're going to condition on all instances for which the predicted probability of the kth class is alpha, and then we need to observe that class also alpha percentage of the times. And that's a condition that you want to have. So in the estimator, what changes there? Not that much. The only thing that changes is that we have now here an additional sum over all the classes. And the binning is now going to be redone for every class separately. So you take the first class, you look at all your predicted probabilities for that class, you divide it into different bins, you compute the difference, then you do it for the second class and so on. So that's what changes. And then we have a third definition of calibration, and this is called calibration in the strong sense, which is even stronger than this previous definition. And what's the difference here is now we're going to condition on a complete probability vector. So we say that for all the instances for which our predicted probability vector is the vector S, the probability that we observe class K in our data set needs to be this value, the kth value of this vector Sk. So this is different from the previous definition where we conditioned on all the probabilities of a given class that needed to have a value. Now we condition here on the whole probability vector simultaneously need to have a specific value. And doing kind of estimators here that are based on binning becomes challenging. Some people have tried to do that. So in this paper, which is actually a recent paper, they propose binning actually as a kind of baseline. And the problem is that now you have to do binning multidimensional. You have to do binning over the simplex. So this is here an example. It's a picture from that paper where you see all those triangles here. So it's a three-class problem in this case where the probabilities are in the free simplex. And you see already that some bins, there's very few observations in some bins, even though this is not a very small data set. Some of the bins really become infrequent, and that's a problem with binning there. So typically for this type of calibration, we're not going to use binning anymore. And that brings me to the next slide, where nowadays there's a tendency to look at estimators for this calibration that are not based on binning. So to introduce these, I need a bit of a different notation. So we're also going to encode the true label Y as a one-hot encoding. So for example, if we have 7 classes in total, and it's an instance of class 3, then we have at this third position a 1 and all the rest is zeros. So then in this paper that I had on the previous slide and also on top here, they define a calibration error as follows. It's actually quite similar to this notion of strong calibration that we had on the previous slide, but it's now defined as follows. So we take an expectation over the X, and then we take also an expectation over the labels when we have observed the X. And what you see here is on the right-hand side, the predicted probability, and on the left-hand side, the frequency of seeing a particular label for all the instances that have a given probability. So this is exactly what we had on the previous slides, where it was an equality that needed to be satisfied. Here you just subtract the two from each other, and ideally you want this thing to be 0. So you're going to be calibrated if this quantity here is 0. But it's again a quantity on the population level, so we don't have access to the underlying distribution, so this cannot be computed. So how can this then be estimated? So there are several estimators proposed in the literature, but this recent paper has quite an interesting one to my opinion. So what do they do is this first expectation here over the distribution is replaced just if you have a validation data set by your n data points in your data set. And then you still have to approximate as well this expectation. So they propose an estimator for that. And what is this estimator? It's an estimator that avoids binning. You do some kind of a local approximation with a kernel. It's a specific kernel they use. So what you see here in this kernel, it's a similarity between two different probability vectors. So instead of separating the space into fixed bins, you look for a given probability vector. What are the vectors that are close to it? You measure it with a specific kernel function, and in this paper they use a Dirichlet kernel. It's not very important. They can prove some consistency results for this specific kernel, but just think of a kernel there. And you look basically at in this neighborhood what is the label vector that you observe in that neighborhood, and that's basically your estimator. So you have in fact replaced this binning by something that's more smooth. And an additional advantage of this is that if you want to optimize this, this is going to be easier than those binning measures, which are hard to optimize with numerical optimization routines. Okay, we have seen now several measures of calibration. And then the next question is, okay, you get then such an estimator, you get a value. Is my model now calibrated or not? And then people have developed different statistical tests to evaluate whether your model is calibrated. I only have time to discuss one of these tests. It's a general test that was developed some years ago by Vicena-Vicius, and it's based on bootstrapping. So what do? You have a validation data set, and you're going to take bootstrap samples from that validation data set in the first step. So for example, you have a validation data set of 100 data points. We're going to sample with replacement maybe 1,000 times again a new validation data set of 100 data points. In the next step, we throw away the true labels of all those data sets. We're not going to use the true labels, but according to our predicted probabilities, we're going to sample new labels. And we're going to do that to build up a null distribution, a distribution under the assumption that the null hypothesis is true. So then for each of those data sets, you now have new labels. You're going to compute your estimator of calibration. So that can be anything. This can be this expected calibration error that we have seen that relies on binning, or it can be this kernel-based calibration error that we had seen on the previous slides. And then you get a distribution of, an estimate of the null distribution, the distribution under the assumption that the null hypothesis is true. And this is going to be the distribution that I plot here on the right-hand side. And then in the last step, you take your original validation data sets, you take your true labels now, and then you compute this statistic as well. And you're going to look where it lands at this distribution. So here in this example, this might be the red line that you see on the right-hand side. If the probability to observe the true labels under this distribution is unlikely, so if it's very far to the right, then you're going to reject the null hypothesis given the significance level that you have defined before. So that's how this test works, and it can be used with any calibration measure. Okay, so if the outcome is that your model is not calibrated, then especially in the ECML PKDD community in the last 5 to 10 years, people have developed a lot of methods to recalibrate your model. I don't have time to go over all these, but what those methods typically do is they take your predicted probabilities and then they define a mapping to convert them to new probabilities. So basically a function that takes the predicted probabilities as input and gives new probabilities. So here in this example, this is for binary classification. I've visualized here two different models, isotonic regression and beta calibration. So typically those methods differ in the type of functions they consider to remap your probabilities. And that's typically by a fitting procedure. So you know the observed frequencies for a validation data set. So you're going to remap your probabilities so that they more correspond to the observed frequencies. So that's how you can do that on a validation data set. So this is typically done on a validation data set. However, in more recent papers, there's now a trend to do that already during training. So in deep neural networks, they're typically not calibrated. And what recent papers try to do is to avoid that you need to put aside such a validation data set for it. And it has to be quite a large validation data set. So that's a disadvantage. So there's many methods now that also try to solve the problem during training. And here in this paper, it's quite a simple procedure. So what do they do is you have your traditional risk, let's say cross entropy in neural networks. And you have as additional constraint that your calibration error should be smaller than a value rho. So think of this calibration error that we had without binning, the kernel-based one. That's one that's differentiable. So as you might know from basic mathematics, this optimization problem can be rewritten by using the Lagrange function in this objective function, where we have now a parameter lambda that corresponds to the rho, basically. So you're going to optimize this during training directly. And what this means basically is that you introduce some sort of regularization that avoids this overconfident predictions. So this is typically something that's going to work when your probabilities were something like that you typically are overconfident in the binary case that you predict towards with too high confidence that it's the negative class or the positive class. So for this type of miscalibration, this is going to work quite well. There's other methods in the literature like the focal loss, label smoothing, entropy regularization that all try to do something quite similar. Okay, that's about how to evaluate such probability distributions on the first level. Let me see a bit the timing that we have. I will now move on to the second part. We still stay in the classification setting, but now we're going to use sets to represent our uncertainty. And let me explain on this slide what this means. There's also various frameworks defined here. So let's come back to this neural network example. We had this flower that we put as input to our neural network. We had our softmax function, and the predicted probabilities were something like that. If you just make a prediction of what the class would be, you would take the highest probability, and that would be your prediction. Now, in the set-based evaluation framework, you're not going to predict one class, but you're going to predict multiple classes. So in this example here, there's two probabilities that are quite high. So you might predict here a set that consists of two classes, and then you say, my true class is one of those two classes that I predict. So in the PhD thesis of Titouan Laurier a few years ago, there's quite a nice distinction of all those frameworks. So you have frameworks that focus on the size of the sets. So you want to have control of the size. So a very simple example is like top K prediction. You predict the top 5 classes, but there's other frameworks as well where basically you have constraints on the average size. So for instances where you're very certain your set might consist of only one class, and then for instances where you're very uncertain your set might consist of multiple classes. And then you have frameworks based on error control, where we want to have some guarantees on the error that we make. Conformal prediction is nowadays a very famous example of that, and I will discuss that a bit more in detail. And then you have also frameworks that do a compromise of the first two, where you have specific utility functions that have a trade-off between correctness on the one hand and the size of your set on the other hand. And I will also talk a little bit about that. So let's start with conformal prediction. So what does conformal prediction try to do? It's rooted in the classical hypothesis testing framework of statistics. And if you have, for example, this image here, it's not so clear what kind of number it is. So for this image, you typically would predict a set that consists of more than one class. For example, you would predict the set that consists here of the classes 2, 3, and 8. By the way, I will always use the capital Y for the set notation. And conformal prediction, what it's going to do is going to give you some guarantees on the error you make. So if you say, I want to have an error of maximal in epsilon % of the cases I don't have the correct label in my sets, well, conformal prediction is going to be a framework on how to construct those sets so that you have in maximum epsilon % of the cases the fact that your true label is not part of the set. So how does this work? A central aspect of conformal prediction is the so-called nonconformity score. And a nonconformity score, intuitively, I have an example here of a data set, is a measure that's going to look at how likely a given class is the true label for an instance. So for the example here, we have this one with the circle. It could be class 0, for example. It could be class 1. It could be class 2. Well, some classes are going to be more likely than others. When you look at the data, there's no other class 0 examples close to this example that you have. So it's going to be very unlikely that it's class 0. And what this nonconformity measure basically is measuring, it's looking at how much, for a given prediction, how much it conforms the data. So yeah, the notation I'm using in the presentation is for a nonconformity score, it's a function f that takes your x as input and then a label that might conform to this. And for classification, yeah, the kind of standard nonconformity measure that's used is a very simple one. It's just the minus of the predicted probability. Because for a probability, the higher the probability, the more likely that it is this class, but you want the opposite in a way. It's a non-conformity measure. So that's why you take the minus of that probability. There's other measures used in the literature, but this is like the most used and it's also quite intuitive. And then what you're going to do as a next step is on a validation data set, you're going to look at the distribution of those non-conformity scores. So I have here a validation data set of endpoints. For each of these endpoints, I take the true label. It's a validation data set, so I know the true labels corresponding to those data points. I compute those non-conformity scores, and I build up the empirical distribution of those non-conformity scores. And then if I want error of maximum epsilon, then I'm going to look at a probability mass of that distribution, which is at least 1 minus epsilon. So the green part that you see on the slide. And that's going to be actually, it's a quantile that you compute of that distribution. That's going to be our threshold that we then going to use on test data. So if we then have a new data point that's coming from the test set, a new data point for which we don't know what the class is, what is the set that you're going to predict? We're going to consider all the possible labels y hats. And if the nonconformity score is smaller than this alpha 0, this threshold that we have found, then we're going to include that in our set. And if you construct the sets in that way, it should be kind of intuitive that you will have this error guarantee. Of course, under the assumption that the validation data and the test data come from the same distribution. So here is an example of a simulation that one of my PhD students did for me for this presentation. What do you see here on the horizontal axis? We have on the horizontal axis the size of the validation data set. And then the two pictures are for two different sizes of the test set. So on the left-hand side, we have a test set of size 3000. On the right-hand side, we have a test set of size 300. It's a synthetic data example. There we can do resampling. And then on the vertical axis, we have the coverage level. So in this example, we asked for a coverage of 90%, the red line. So what you typically see is that for a fixed validation data set and a fixed test set, we don't always achieve that coverage, but in expectation, we're going to achieve that coverage. You will also see that because the test set is smaller on the right-hand side, you see that also the deviation is bigger. So actually this coverage level, recent literature has shown that this follows a beta distribution. So if you interpret what this coverage actually means, it's actually a coverage on expectation when you take the expectation over all possible validation data sets and test sets. We don't have a guarantee for an individual validation data set or test set. Okay, that's all about conformal prediction. Let me see a bit what the timing is. I thought the coffee break was at 11, but I hear already a lot of noise in is the poster session. Okay, so let me finish maybe the second part and then we can take a break at 11. The coffee break was officially announced at 11, so we still have 10 minutes for that. So this third framework, I've discussed about conformal prediction to predict sets. Now this third framework is utility maximization. And what are we going to do here? It's slightly different. We again going to use those predicted probabilities as our instrument to construct a set. But we are now going to construct a set that minimizes a specific utility function. So I have here a utility function U that takes the ground truth class C as input and my predicted set Y. And we're going to, the predicted set that we're going to construct is going to be the argmax of this utility function. On my next slide, I will also use a shorthand notation. It's an expectation here over this conditional distribution. The expected utility, I will use this notation for it. So what are the typical properties that such a utility function need to have? So what we minimally assume of it is that if the true label is not in the predicted set, then you should return a utility of 0. You didn't predict the true label in your set, so you should not get any reward for that. And then if the true label is in the set, then we're gonna have a reward that depends on the size of the set. And this reward is expressed by this function G. The function G, we assume that we have a reward of 1 when the set size is exactly 1. And then it should be a decreasing sequence. If we predict a larger set, the reward that we get should be smaller. So classical measures for this reward function or utility score are precision, where you just divide by your reward by the size of the set, and the F beta measure, where beta is a hyperparameter that takes your reward in a slightly different way. I have to say, theoretically, this one is not very useful because we can show that the optimization problem here, it always leads to sets of size 1, so you don't express your uncertainty well there. So this F measure, for example, is a better one. There's others, more specific measures also proposed in the literature. So let's take an example on a concrete case. So we have again this flower, and let's say for this flower, the predicted probability distribution was this predicted probability distribution over in total 1, 2, 3, 4, 5, 6, 7, 8 classes. I've sorted already the probabilities. So we have shown in recent work that actually by just sorting the probabilities and then looking at what is the reward, the expected utility, if you only return a set size of 1, the highest probability, and then looking at the probability, the expected utility when you return a set size of 2. So in this case, the reward is higher. And you continue then by looking now at the 3 most highest probabilities, and you again look at the reward. Here, the reward decreases, and then the theory says that we can stop here, that we have found the optimum of the optimization problem. So we stop here in the third step, and our set that we return is here we return a set consisting of 2 classes. Here are some examples on real-world data sets. So on the MNIST data set, with this F measure as your reward function. So the number 8, it's quite clear that this image is of class 8. So the set that you return just consists of your prediction 8. Here for this image, it's not so clear what it is. So the ground truth was here apparently a 2. So with this F1 measure, you return a set consisting of 3 elements. With the F5, you can return a set consisting of 5 elements. And then another example in this image over here, there's an animal present. It turns out to be a cow, but it's not a high quality image, so it's not so clear. With if you predict the top 5, for example, you'll see that cow is not the highest predicted probability, is the second highest. And with this utility maximization, we will return a set consisting of 2 elements, that's sheep and cow, basically. Okay, I think we are kind of at 11, so I suggest to take a break here and then do my last part after the break. Okay, let's maybe first ask whether there are some questions about so far. Yes, in the back.
I have a question about calibration.
Mm-hmm.
So you mentioned confidence calibration and class-wise calibration, for instance.
Mm-hmm.
And for me, it's often enough to only calibrate the confidence, the top probability, because in most cases we only use this probability and not the rest. So is class-wise confidence really useful, and in which cases?
Yeah, I think if you only need the highest probability for your application, then indeed maybe confidence calibration might be enough. I can imagine there's also applications where you would like to know the full underlying distribution, so then you might also want to analyze those stronger notions of calibration. So I guess it depends a bit on specific application, what you're interested in, what's important for you, whether you would choose those this confidence calibration or this stronger notion of calibration.
Thank you.
So for example, for these frameworks that we discussed at the end, where you build sets on top of the probabilities, so there those stronger notions, for example, might be important because you're not only using the top probability, but you're also using other probabilities. Yes? So which methods do you, yeah, yeah. Yeah, so in language models, I don't think they're used so much yet, but I can see, like, for example, conformal prediction is more and more used in deep neural networks in general. So I think this is something that's coming. Actually, for the moment, robustness of deep learning systems and correct uncertainty of deep learning systems, as also Ike already explained in his part, is currently a hot topic in deep learning. So definitely it's not the case that in every large language model or deep learning framework you have kind of uncertainty quantification, but I only believe that this is going to be more and more important in the future. And to answer your questions about the scalability, so I think most of the methods that I discussed are quite scalable to large data sets. The things like strong calibration, there's an issue with regard to scalability when the number of classes becomes large, because typically when you talk about large data sets like ImageNet, also the number of classes really becomes huge. And yeah, this might be an issue for notions such as strong calibration. But overall, like the methods I discussed now based on sets, these are, I would say, very scalable to large data sets. The algorithms are quite efficient. For conformal prediction, I only discussed the split conformal prediction, which is a specific conformal prediction approach. There's other conformal prediction frameworks like full conformal prediction and cross conformal prediction. These are less scalable to large data sets. Yeah, but I think for each of the categories I discussed, there's at least one method available that scales well to large data sets. Okay. Yeah. Okay, I will repeat for the people online. So the question is about adversarial training. So I think the goal of adversarial training is a little bit more specific. You really want to improve robustness in regions that are close to the training data that you have observed. If you take small perturbations of your instances, you don't want to change the labels basically. So that's a kind of very specific robustness that you want to incur. It's also a setting which is not an IID setting anymore, unlike the settings that I've discussed about here. So all the methods I discussed here are under the IID setting where your training and test data come from the same distribution. I think maybe Ike, in your part, you will also very quickly discuss about the non-IID setting where at test time you have observations that come from a different distribution. But yeah, so what we discussed so far is actually in the IID setting. Other question? Maybe it's good to use the mic.
Thank you. For this calibration methods, does they also work with regression problems, or is this kind of problem?
Yes, and this is what I'm going to talk about after the break.
Oh, okay.
Yeah. But for regression, it's less common to do calibration. Yeah. There was also a question here.
Thank you. So for the case where we have a lot of classes, I think to get to a certain like guaranteed accuracy, you would need to predict more classes. So does this conformal prediction scale well in the case of many classes? Because it seems like then the probabilities will be more spread out over all of those classes, so it will become harder to...
You need to compute this non-conformity measure for all the classes then. So I would say it scales linear in the number of classes. So
Okay.
yeah, if you have 1 million classes, okay, that might still take quite some time. But yeah, that's how it scales.
Okay.
Where you have principal and infinite number of translated to support, then you don't do this.
Yes, because you do it on the level of the residuals. So
You have a structure of
I haven't seen any papers that try to do that in the classification setting, but if you really have, if you have very large label space in classification, there might be some issues there. All right, so I think it's now after 11, so I suggest that we take a break here of 30 minutes and we meet here again at 11:30. I still have a very small part to present and then it's going to be Ike's turn. Okay, thank you for coming back. So I still have a small part to go, so we mainly talked about classification. During the break, several people asked me what's now the link of what you discuss with aleatoric uncertainty. So I will now move to regression, and actually my next slide has a nice example of it. So in the probability distribution that we have for classification is in binary classification a Bernoulli distribution, and in multi-class classification a categorical distribution. For regression, this becomes more complicated. So you again analyze the conditional distribution, the distribution of the labels given X, and for example in the standard linear regression model, this is a Gaussian distribution where for every X you have the same variance, so it's a homoscedastic model in fact. And it's actually this first order distribution that's your representation of your aleatoric uncertainty. So here, if this Gaussian is a very wide Gaussian, if the variance is high, then your aleatoric uncertainty is high. If this variance is small, then your aleatoric uncertainty is small. That's why most of the methods I've discussed so far are mainly focusing on this aleatoric uncertainty, unlike the methods that Eike will be discussing, where we will also have second order distributions that can more distinguish between this aleatoric and epistemic uncertainty. So the distribution is this representation of your aleatoric uncertainty, and I've mainly been talking about how to evaluate this distribution correctly. Now, maybe Eike, could you close the door for me? So for regression, the situation is a little bit different than for classification. You again have extensions where you're going to look at whether this distribution is well calibrated, or we can look at sets as well. And yeah, for classification, I would say calibration is kind of more used in the literature, whereas for regression, the set approach is more common, and it will have the specific flavor in a lot of methods of prediction interval that you're going to construct. So let's first look at the extensions of calibration. So there have been a few methods proposed in the literature. There's not that many papers, but the papers that have done those extensions of calibration, they typically look at the quantiles of the conditional distribution. And so you need to have a quantile function of your conditional distribution. So this is this QA. It's a prediction of the quantile, the alpha quantile, and it's conditioned on X. And in probability for the true labels that we observe, so we take again this probability over the underlying distribution, both over X and Y, then the probability that Y is smaller than the predicted quantile needs to be exactly alpha, where we have specified this alpha quantile. So that's a kind of natural extension of calibration as we had it for classification for regression. And it looks like a strong condition because we want this to be satisfied for all the quantiles if we have this conditional distribution, but actually it's quite weak. So this first paper has a nice example. So let's assume a distribution where the ground truth is as we have on the left here. So it's a kind of sine wave where the variance increases more to the right. So it's a heteroscedastic setting. But if you fit a linear regression model to it, that's what you see in the middle picture. So you have this linear regression model is this line that goes up, and you have your Gaussian distribution with a certain spread that's kind of modeled with the colors. So it's quite a bad fit for this problem. But if you look at the modeled quantiles and the quantiles that you obtain, you will see that they're quite well in line with each other. So we have here on the horizontal axis the quantile level that we assume, and then on the vertical axis, because it's synthetic data, we can measure how many times the true label Y is smaller than the predicted quantile. And you see it's quite close to the diagonal. Just like with the reliability diagrams, we want to be close to the diagonal. So even though this is really a bad model in terms of calibration, it's quite strong. So these are some extensions. Instead of fitting such a conditional distribution, so on Monday we had this tutorial on time series forecasting. I have now only given this example of linear regression. There's many other complicated machine learning models that fit other conditional distributions. For example, if it's not exactly Gaussian, you have mixture of Gaussians. Of course, if your relationship is nonlinear, you can introduce a neural network instead. If you have count data, you might use a binomial, a negative binomial distribution as your underlying model class. Normalizing flows are nowadays quite popular. So there's a wide range of models. I'm not going to talk about that. But instead of fitting such a conditional distribution, if you only need the quantiles, you can also try to fit a model for those quantiles directly. So instead of having a regression model for the mean, we can have a regression model for the quantile. And that's typically you do that by optimizing the so-called pinball loss. It's a specific loss function where we have take a maximum over two components. So you have here Yeah, this difference, the predicted quantile minus your y, and then the opposite over here. So only one of the two terms can be positive, and they have a separate weight, those two terms, based on the quantile that you want to model. And so if you optimize this loss function, instead of estimating the mean, you're going to estimate a quantile, and then you can directly also assess this calibration for different quantiles. Or you can do what is for regression the more common approach to construct a prediction interval. So what you see on the right-hand side is already some sort of prediction interval. I've modeled the 10th percentile quantile and the 90th percentile quantile. Everything that's in between is going to be my prediction interval. So for regression, the set-based representation that we had for classification kind of becomes now in many models becomes an interval. Not always, but in most models it becomes an interval. Okay, so for those intervals, so I will use the general notation as follows. I have a predictor gamma, that's a mapping from X to all closed subintervals of the real line. So that's the notation I use for that, for the model. And then we want a couple of properties of such an estimator. First, we again want some sort of guarantees in terms of coverage. Here it's typically called in the literature marginal validity. This means the probability that a random y and a random x, that the label y is in my interval, I need to have a coverage of 1 minus epsilon. It's a kind of guarantee you want to have. If you take, you only want to have in epsilon percentage of the cases that you're outside your predicted interval, then you want to analyze this coverage guarantee. So I would like to remark that calibration, as on 2 slides before, is a kind of strong condition, because there we had an equality. Here it's larger than, so it's a weaker condition. And we now do that on the level of the interval, whereas before it was on the level of individual quantiles. And then an additional measure that you might be interested in is in how large this interval is. And if you have a larger interval, again, your aleatoric uncertainty will be higher. If you have a small interval, your aleatoric uncertainty will be smaller. So that's also the average width is something you might be interested in. And so there's really a lot of methods in the literature that can produce those intervals. So any conditional density estimation methods, but also like direct interval estimation methods, such as what we have seen, quantile regression. There's also ensemble methods, for example, that do that. And you can also do this with conformal prediction. And that's what I now want to explain in my last slides, how to extend conformal prediction for this. So we are again in the split conformal prediction scenario, where you have a validation data set on which you model this distribution of nonconformity scores. And the only thing that differs compared to classification and conformal prediction is that you're going to have different nonconformity scores. So if a row is a predictor, could be a predictor of the mean, or could be a quantile, or the median, could be whatever. A standard nonconformity score is this one, what's called in the literature the absolute residuals of your model. This is standard use. Now, in some recent work of one of my PhD students, we have shown that for heteroscedastic data, actually this nonconformity score works better. So for heteroscedastic data, the variance is a function of x, and you can estimate this also with various techniques, such as mean variance networks, for example. So if you use this nonconformity score, you will get better intervals that are for which your guarantees are stronger over a wide coverage of the X space, the feature space, basically. And then for methods that have already a prediction interval, yes, here we are. There's a specific nonconformity score in the literature, which is this operator, where we take the difference between the lower bound of the interval and my true label y, and then the y and the upper bound. So actually only one of these two can be positive. So either if my true y is above the upper limit of my interval, then I'm penalized for it. If I'm below the lower bound, I'm also penalized. And if I'm in my interval, then this nonconformity score has quite a low value. So that's the only thing that changes in conformal prediction actually for regression. So to give you an illustration, it's a table or a figure coming from a recent paper of us. I have here an illustration on 10 data sets. On the x-axis, we have 10 different data sets. They are sorted according to the R-squared, which is a standard measure of the predictive performance. So this is the thing here in yellow. For those 10 data sets, this first data set has a very low R-squared, and then it goes up. And in blue, you see the coverage that you obtain with quantile regression. We are here interested in 90% coverage, and you see that you're really not having this 90% on average. For some data sets like this one, for example, you're much below it. And in green, I'm showing the average width of the interval. So all the data sets, the response variable was kind of scaled. So they're on the same scale, but you see that also the average width is something that varies quite substantially from one data set to another data set. So if you apply on this conformal prediction, then you get this. So we can have now in blue our coverage level, and we see that we are now here on average really achieving this 90%, this guarantee that we had with conformal prediction. As we have seen for classification for an individual test set, we might be above it or under it, but on average we have this guarantee for all the data sets that we have. So that's why this conformal prediction has become now quite popular as a post-processing technique to make sure that you have certain coverage guarantees. Okay, to wrap up my part. So in my part, I've talked about how uncertainty can be represented by a first order representation in the form of a probability distribution. And actually the entropy or the variance of that distribution is kind of a quantification of your aleatoric uncertainty. And I've also discussed how we can then build prediction sets on top of those probability distributions. I would argue that for classification in the literature, people more work with those distribution and less with sets, whereas in regression, to use sets is very natural and they come in the flavor of prediction intervals. So as I said already, this first order representation is mainly focusing on aleatoric uncertainty, but this is not exactly true because, for example, in conformal prediction, we have also seen the effect of a limited validation data set and a limited test set. So this is not 100% true, but on this first order representation, we're mainly looking at the aleatoric uncertainty, I would say. And a last thing to say is that, yeah, there's not really a way to separate the aleatoric and the epistemic uncertainty in many of those approaches. And that's going to be different with what Ike is going to present, where we will have a more clear separation between the epistemic and the aleatoric uncertainty in the methods that he will be discussing. So are there any further questions about this? We are a little bit running over time, so, but if there's one or two quick questions, we can maybe handle this. No quick questions, then I will hand over to Ike. Of course.